Cool. Tēnā koutou katoa. Good afternoon, everyone. I'm Michael Winikoff from Victoria University of Wellington, and I have to say that I'm not part of the evolutionary computing group. I'm probably the one person who's not. So what I'm going to do in this short talk is give you a little bit of a taste of some of the work that I've been doing and continuing to do. So the context here is how can we engineer autonomous systems, and when I'm talking about autonomous system, it's a software system that makes decisions, takes action in the real world, and where there are usually going to be some consequences if those actions are inappropriate. And there are a whole range of these sorts of systems, some of which are embodied, robots, self-driving vehicles, and some are not embodied, things like smart personal assistants. And all these sorts of systems are rapidly appearing. And one of the challenges is trust. If we're going to use these systems where they do things, and if they get it wrong, there's a consequence, we need to be able to trust these systems appropriately. So one of the overarching questions is how can we engineer these systems so that they have the right features that allow us to trust them appropriately, not under-trusting, not over-trusting either. And this is not something you can come back and retrofit. You have to actually engineer certain features in, like the ability to explain why they've taken certain courses of action. Now, there are lots of different factors that can affect trust. Today, I'm going to briefly mention only two of them: verification and explanation. Now, the need for verification and also certification is fairly clear. If there are consequences that may include damage to property, financial damage, or even risk to human well-being or life, then of course you want to do everything you can to make sure that the system will operate appropriately. And there are a number of specific challenges that arise with autonomous systems. One of them is at the moment you start moving towards full autonomy, you have to deal with not just the expected usual cases, but also a whole raft of unusual cases that can be really hard to anticipate. So if you imagine a self-driving car, a usual case is driving along, following the road rules and anticipating what other drivers might do perhaps. An unusual case might be, well, what if there's been an accident and there's a police officer who directs the car to travel on the wrong side of the road to get around the accident? And a whole raft of other things. So how do you deal with those in terms of behaving appropriately and then also verifying? Specifying requirements is obviously also an ongoing challenge. So there's one paper with a number of collaborators where we made a number of contributions in this space. One of them is to propose a three-layer autonomy framework that separates out the dealing with the usual situations from dealing with the unusual cases where you have to go back to principles and maybe even ethical frameworks, and some stuff for identifying, a process for identifying requirements, and also a number of challenges to researchers, engineers, and regulators. And one of those challenges relates to explanation. So Andrew talked earlier about explanation. What I'm doing here is slightly different in that I'm not explaining the outcome of a learning process, but the behaviour of a system. And this is obviously important for trust if the system does something that might be perfectly correct and appropriate, but is unexpected. So the GPS suddenly says, turn right here. And you're like, I wasn't expecting to turn right. Why is it doing that? If it could also say there's been an accident ahead or there's unexpected congestion, you might say, oh, that makes sense. And it's also useful when you're trying to coexist with these systems. Understanding how they operate allows us to work with them more effectively. So the high-level picture here is you have a system that uses some sort of internal representation to decide what to do, and it uses that to generate explanations. And some of the high-level questions we have to answer to provide explanations include things like, well, what do the explanations look like? What concepts do they use? What do the questions look like? You might want to ask, why did you do that? But also, why did you not do something else? Why did you believe this to be the case? How do you generate the explanations? What form of internal representation do you use? And what are the right sorts of explanations that allow humans to understand systems? So in the work that I'm doing with colleagues, we start off by saying, how do we as humans explain our actions? And then can we allow machines to explain their actions using the same concepts? And it turns out that there's a lot of research in the psychology literature, and some of the concepts that we use to explain ourselves map quite nicely to concepts of the BDI, belief, desire, intention, architecture for agents. So explaining in terms of goals, in terms of plans, and in terms of certain types of preferences. So the hope is that eventually when we have self-driving trucks that sort of leave people, and there are songs written, the truck can at least explain why it left that person. So thank you very much, and this is just some papers and some of my collaborators.